Welcome to a video instructional tape on the subject of coupler curves. I'm Professor Robert Norton from Worcester Polytechnic, and we're going to tell you a little bit about the very ubiquitous coupler curve of 4-bar and 5-bar linkages. Coupler curves are generated by what I think is the most interesting link in a 4-bar linkage, not surprisingly called the coupler. It's interesting because it has complex motion. So every point on that link is, or any line on the link is going through a combination of translation and rotation as the linkage moves. Whereas the other two links that move in a 4-bar, for example, being the crank and the rocker, have pure rotation. And we can have an infinite number of points on this coupler, or on any link for that matter. And any one of those points will generate a curve that, in general, is a tricircular sextic. That's just a fancy terminology indicating that it is of 6th degree, and it can have 3 loops. That's the tricircular designation. A fellow named Knoll, back in 1975, made this comment, which I thought was interesting. He says the coupler curve equation is very complex and no other mathematical result has characteristics matching those of a coupler curve. So it's a fairly unique mathematical entity, at least in his opinion. As I said, you can have an infinity of coupler curves with any one 4-bar linkage, and since you can change the link lengths, that means you have multiple infinities of possibilities. This diagram shows a 4-bar linkage, crank, let's assume it's a crank rocker, so I can call this a crank, pivoted at O2. So that would be link 2. The link 3 is this entire mess of holes. Link 4 is the rocker over here, pivoting it to ground at this point on link 3. Now we typically draw these links in the textbooks as lines connecting the points, and that may leave the student unaware of the fact that the link can extend in all directions to any degree and doesn't change the kinematics. The kinematic motion is defined just by the point-to-point lengths of the links that comprise the linkage. But we can extend those rigid body links in all directions as much as we like, which I've done here, and I've peppered it full of holes such that I could conceivably put a pencil through that hole, move the linkage through its motions, and it will trace the curve that we're talking about. These curves come in a variety of shapes, and I've taken to giving them names here. Highly technical names, as you can see, such as kidney bean, banana, crescent, teardrop, and so on. These are just representative of the kinds of shapes you can get from these coupler curves. Some of the more interesting features that are useful from an engineering standpoint are the fact that many of these curves have an approximate straight line segment. You cannot get an exact straight line with 4 bars. You have to go up to 6 bars or a geared 5-bar to get an exact straight line. But for engineering purposes, these 4-bar linkages can give you a sufficiently accurate straight line in many cases. So I can get a pair of those on a given coupler curve, or a single one. Another useful feature is the cusp, and also its cousin, the crew node. These are sometimes termed double points. It's pretty obvious in the case of the crew node why that name is applied. It has 2 slopes, 2 velocities. Depending upon which direction you approach that point on the plane as you come through it on the coupler, you will have a different velocity, obviously, whether you're on this path or that path. That's where the term double point comes from. The cusp is a point which has 0 velocity instantaneously. So as I traverse this curve, I accelerate smoothly to 0 velocity, and then I accelerate away in a different direction. This is potentially useful for stamping operations or pick and place where I want to pick a part off of a feed chute or something like that. I can have as many as 3 cusps or 3 crew nodes, or any combination of 3. For example, this shows 2 crew nodes and a cusp, and this shows 2 cusps and 3 cusps, respectively. Now, I'm going to demonstrate these with a few models to you so you can get a little sense of how these curves are generated. So what I've done is I've made up some simple cardboard models. And just as in my sketch, I've punched the coupler full of holes so I can trace with a pen. So this is my link 2 here. That's instance center 2, 3 right there. That, of course, is a coupler point. But that's going to trace a circle. This is a Grashof linkage, by the way. So if I take that particular coupler point, why is it a coupler point? Because it belongs to link 3. It's also instance center 2, 3, so it also belongs to link 2. So it's sort of schizophrenic. As part of link 2, it's being forced to rotate in a circular arc about instance center 1, 2 down here. And thus, this is a degenerate coupler curve in our sense of 6th order curves. It's degenerated to 2nd order, or 2nd degree, I should say. However, if I take a point, say here, and I trace its curve, you can see it has somewhat more interesting shape, sort of a flattened ellipse. It's partly hidden by my cardboard, but if I move the cardboard around, you can get a sense of it. In general, points close to instance center 2, 3 are going to be relatively uniform in shape, being somewhat elliptical. This guy over here is going to have a bit of a flat on it. It's, again, being hidden a bit by itself, but there's the flat side. So that's a bit of a single straight. And if I go perhaps out to the end here, I can get something looking sort of like a flattened kidney bean kind of shape, also having something approaching a straight line segment here. So that gives you a little sense of the kinds of shapes you can get. Now that happens to be a Grashof. I have another example here of a Grashof linkage in cardboard. I don't have quite as large a coupler on this, so it makes it a little bit easier to see. I don't hide so much of the curve, but just to, again, to prove to you that this is in fact Grashof, I'll make that go around in a complete circle. If you've seen the Grashof tape, then you know all about that. And by that same token, this point over here, which is instance center 3, 4, if I backdrive the linkage from the rocker, that's in fact a coupler curve because it belongs to link 3, but it's another one of those degenerate versions because it's gone down to 2nd degree by reason of the fact that it's also constrained to pivot about instance center 1, 4 down here in pure rotation. But now, I've extended the coupler up here with a piece of cardboard and punched some holes in it. So if I drive it from there, I get something of a kidney bean shape there. These are going to be fairly similar to one another because they're so close together on the coupler. But I made the small coupler, as I said, so you could see the curves without too much interference. So there it gives you some sense of some variety of shapes that you can get. And you should not be surprised by the fact that given a Grashof linkage in which one link can make a full circle, these are closed curves. The coupler curves all close. Now let's take a non-Grashof linkage as an example, also made in cardboard, and see what we can do with it. Well, let's determine to your satisfaction that it is in fact non-Grashof. There, my hand's in your way, but if I do this with my non-dominant hand here, if I can get that through the hole, my pen isn't going through for some reason, but you can see that I'm going at a toggle, so that cannot go any further that way, and if I go this way, it's going to toggle over here again. So I definitely have a non-Grashof linkage. I can't make a full revolution with any link. But if I now go up on the coupler and I grab one of these points, let's say I take the one furthest out here as a starting point, and I try to drive it up here, I'm going to help the links through the toggle positions with my other hand here. Okay, let's look at that one for a minute. My hand wiggled a bit at the top there. There shouldn't be double lines. It should trace exactly the same curve on each traverse. Now here we have a more interesting looking curve. This is a non-Grashof linkage. No link to make a full revolution, but note number one, we have a closed curve, nevertheless. So the coupler curves will be closed irrespective of the Grashof condition of the linkage. Number two, we seem to have two cusps, one here, one there, and some interesting shaped curve in between. Let's try this point here and see what happens. Again, I'm helping it through the toggle points with my other hand. And there's a little bit of give in the cardboard accounting for the fact that I don't have exactly the same traverse when I come back over it the second time. And again, since these points are all fairly close to one another on the coupler, I'm seeing what definite family resemblance from one to the other. I'm still getting some cusps down here, and finally down there. Okay, here I got a crew node. I was looking for the crew node. I knew there was one in here someplace. So this one gave me a crew node, and some of the others gave me a cusp. So that gives you some sense of what we can do in terms of shapes for these curves. But how do we find a linkage that gives us a curve of the shape that we like? Typically in a design situation, we're coming at this from the other direction. We're not just arbitrarily picking a linkage and saying, oh, aren't those coupler curves pretty? We typically have some idea as to what we would like for a shape of a curve, perhaps, and we'd like to find the linkage. This is the inverse problem. And it turns out it's a relatively difficult problem to solve. And what makes it easier to find such a linkage is to have a collection of curves drawn by linkages of various dimensions, and that exists in several forms, one of which is this so-called Hrones and Nelson atlas. And I have that atlas here, and in a moment I'm going to go into it and show you how to extract the information. But before I do that, I want to give you a little preview of the way it's arranged. This is a figure out of your book, Design of Machinery, and it shows one page out of that atlas, and you can see that it shows a linkage. It's a little hard to see at this scale, but there are two circles in that place, and that indicates a fixed pivot. Single circle indicates a moving pivot. So this would be link 2 right here. That's instead of 2, 1. This is coupler, line to line, line from pin to pin. This is the rocker. This is the ground link. And these points right here are just like my holes in my cardboard. They're points on link 3. The surround is not drawn on the picture, but they're physically part of link 3. And you see quite a collection of different curves. Here's a cusp, there's a crew node, there's another crew node, there's a crew node, there's a cusp, etc., etc. How do I extract the linkage information from this book? I'm going to show you that in detail in a second, but in general, this is the approach. Here I've superposed the linkage on the atlas page for this particular curve that looks like a bit of a figure 8. That's the point generating the figure 8, so I have to encapsulate that in my coupler. So I show the coupler here with a triangular shape. I've heavied in the links. There's link 2, link 1 I show dotted, link 4, and the actual pin-to-pin dimension of link 3. Now up here in the corner, not visible at this scale, but you'll see it clearly in a minute, is a little chart on each page that tells you what the link ratios are. In this book, every crank is considered to be 1 unit long, and he gives you the ratios of the other link lengths with respect to that. So let me go now to the book itself. This Hrones and Nelson atlas is long out of print. It was done in 1951. But I've obtained the publisher's permission to reproduce it as PDF files. And they've been scanned, and they're on your DVD in your book. So you actually have access to it and can use it for your assignments if your instructor so wishes. So now let's go look at the book. Analysis of the 4-bar linkage. Very old book. It's by Professor Hrones and Mr. Nelson, Professor Nelson, I guess also, of Massachusetts Institute of Technology, and it's done in 1951. And this actually was Nelson's thesis. Back in 51, of course, there were no computers, and the only way you could generate these curves was to mechanically create them. So they actually made the links. I want to show you this figure down here in detail, right here in the corner. This is the way they've arranged the atlas. So here you see link 2, link 4, and an expanded coupler, much like my cardboard model, which is peppered full of holes. And they typically have 5 rows of 10 holes each on each linkage. And they're going to iterate the link dimensions, i.e. the link ratios, as you go through the book. So on any one page of the atlas, you will find a linkage of a particular set of ratios, that is the ratio of the crank to the couplet to the rocker to the ground will be certain numbers. And on that page, you will see one of these rows of dots generating their coupler curves. And then as you turn to the next page, you will see the next row, and they typically start at the top row and work down, and then the third row and the fourth row and the fifth row. So for every particular linkage geometry, there will be 5 pages in succession that show you the curves of all 50, 5 by 10 typically, coupler curves. The total is something of the order of 7,000 coupler curves represented in this book. I don't have an exact count, but it's in that ballpark. So let's move to a page that has the information on it. I will just go to page 1, I guess, and start at the beginning. A very good place to start. Okay, so here's the whole page. We can just focus in on this bottom piece here, I think would be fine. Give an overview first. So this looks much like the figure in the book that you've just seen a moment ago. And up here in the right-hand corner, let's zoom in on that so we can see that a little more clearly. Thank you. That's better. So here we have a little diagram. He doesn't bother to draw the surround of that link. It's not necessary, but that's like the diagram I showed you a moment ago. That's the extended coupler, and it has the 5 rows of dots representing holes, if you will. The ratios here, A, B, and C, here all being 1.5, represent the lengths of the coupler divided by the crank. That's A. B is the rocker divided by the crank, and C is the ground link divided by the crank. So that's pretty easy. And recognize that these things are scalable, so that if you were to double the size of all the links, you will get exactly the same curve shapes. Of course, your velocities and accelerations will change drastically if you drive that larger linkage at the same speed. But in terms of the physical shapes of the coupler curves and the positions of the links, the angular positions of the links, those are all scalable. So you can just take these ratios and apply them to any size crank that you desire to get the size of curve that you are interested in. All right. So let me flip through fairly quickly here the first 5 pages to give you reinforce this idea of how they've arranged it. So here we see the curves associated with the top row of the matrix. For some reason in this particular one there are 2, 4, 6, 8. I don't know what happened to the other 2, but many of the pages will have 10. So there's going to be 40 curves in this particular set. So there is page 1. Now we go to page 2. I'll pull that down. I'll get onto the camera. And this is the same link ratios. You can't see them at this scale, but it's still 1.5, 1.5, 1.5. And we've moved down to the second row. The previous page was up here. And we have another set of, in this case, 8 curves. By the way, all of the linkages in this book are Grashof. And if we go to the next page, which is page 3, we now have 8 more curves, and so forth and so on. So this is page, up to page 4. And they actually show you up in this matrix, you see a solid line drawn on the dots to indicate where you are in the matrix of the coupler. So now I'm below the line of the coupler by 1 row. Notice that one row of dots is on the line of centers of the coupler, and there are 2 above and 2 below. So right now we're 1 below. And finally at page 5, we are at the bottom row of the coupler. And our curves are now down here with respect to the linkage geometry. I'll go one more page to show you that, and perhaps now we can zoom in on this little corner again and show that now on this 6th page, we're back up to the top row of the matrix starting over again, but now the link lengths the link ratios have changed to 1.5, 2, 2. They were 1.5, 1.5, 1.5 before. So a new family of links. What I'd like to do now is try by example to show you how I would extract the information from this atlas for a sort of a practical problem. I'll admit I made the problem up, but it's not an unrealistic problem. Let's assume that I have a machine that is making some kind of a product, and it's making it at some reasonable speed, and it's automated, and I want to be able to feed parts down some kind of a feed chute here, perhaps blow them with the air or just let gravity bring them down. It depends on the circumstances. And I want to pick those parts off one at a time, slice them off the bottom of the stack perhaps, and I want to deliver them to a moving conveyor, and I want to transfer them from my gripper, which is not shown here, that's going to pick them off the bottom of the stack. I want to transfer them by some means at the right time in the cycle to a nest of some sort that's on this conveyor, and thus I can do some further operations on that, quite likely add some other parts. I'm making an assembly of something or other here. So my concept that I start with is to say, well, gee, this is a nice application for a cusp because, look, this parts feeder is stationary. It's on the ground plane. So if I'm going to pick something off the bottom of that stack, I've got to be stopped, at least for an instant. And a cusp is exactly that. It stops for an instant. So if I stop just long enough for a vacuum or some other means to suck that part away, I then want to accelerate the part down some path. I don't really care too much about the shape of that path, but at some point I'd like it to become fairly straight. I'm going to darken that in. It didn't show up too well from my previous sketch. So here's my cusp. I'm going to pick it up at the bottom of the parts feeder. And I want to, let's say I want to make it come down, and I don't care too much about the shape of this here. But at some point, I want to get more or less parallel to the conveyor so I can track it. And I also have to arrange things so that I match velocities at least to a reasonable tolerance. I don't have to be exactly the same velocity. I can be for an instant, certainly, but I don't have to be over the entire track. And once I've made the transfer, then I just want to go back home and do it over again. So I get out of here, turn the corner, come back up some other path like so, and back to my cusp to repeat the cycle. So this, my linkage, which is not yet shown here, that's what I'm trying to find, is going to be driven by the same motor that drives this conveyor, such that everything's in synchrony, so that as a part appears in the proper location here, as the nest appears, my part will also appear and be transferred. Okay? That's the idea. So I'm now looking for, in my mind, I'm looking for a curve that sort of looks like Willie the Whale here. Okay? I want to now go into my Hrones and Nelson atlas and see what I can find. So we'll put that aside, and I happen to be sitting at page 7. I'm just going to keep going and see what I can find. So I'll turn it over. I'm not even going to look at the top pages. It's too much trouble to move the book around. I'll just look at the bottom here. So here I see some curves that have not quite a cusp. I don't see a cusp. There's a crew node. No real cusps on that page, and I'm looking for a cusp. Here on this next page, well, there's a cusp. There's a cusp right there. And lo and behold, there's a sort of a flat spot on that. And then it returns back to here. That looks like it might work. So let's try that one. So let's suppose that I'm attracted to that particular coupler curve, and I decide I want to make that linkage. How do I determine what the links should be? That's the next step. So I'm going to use a piece of tracing paper so I don't mark up this rare old book. And I'm going to need some drawing instruments for this too. That paper doesn't quite go as high as I would like, but I think I can get away with it. Okay, that's going to do. That's perfectly fine. Now, I look up on the upper corner here. You can't see it. We won't bother to zoom in, but I'll tell you, this is 1.5 is A, and B is 2.5, and C is 2.5. So I know already the dimensions of my links, and I can let my crank be any value I want. It can be 10 inches, it can be 2 inches, it can be 75 millimeters, whatever I feel like. In fact, if I put my scale on this drawing in the book, I find that it's pretty close to 2.5 inches. So my crank at the scale this book is drawn is 2.5 inches. I'm going to stick with that for the moment just to not complicate things further. So that means that my coupler, A would be the coupler, would be 1.5 times that. So that would be 2.5 plus 1.25. So that would be what? 3.75 inches then. And my crank is going to be the same dimension. No, I'm sorry. I'm misreading it. I meant to say my rocker. That should be rocker. I've already got the crank. The crank I measured. So the rocker here is, this is the coupler. This is the rocker. And this is the ground. So we don't get those confused. So my crank is 2.5. My coupler is 1.5 times that, which is the 3 3/4. My rocker is 2.5 times this. Well, twice that would be 5, and another half would be 1.25. So that sounds like 6.25. And the ground is the same as the rocker, 6.25. So now I have my physical link lengths for an arbitrarily chosen length of crank. Okay, that's easy. That's the easy part. But now I've got to find out where this coupler point is. First of all, I've got to detect what point is generating this Willie the Whale curve that I'm interested in. And you look and see what circle is sitting on that curve, and there it is. I want to locate that with respect to the links. So let me start drawing some things on here. There's my link 2. I'm going to put a little ground pivot thing here to emphasize the fact that that's a fixed pivot. So that in your book would be labeled O2 most likely. And we'll put a pivot over here and we'll call this O4 down here. And here is my link 4. Let's label that as 4. And label it as 2. 2 is going to be the crank, 4 is the rocker. That's the conventional notation that I use in your textbook. And here is link 3. Now this is the line of centers of the coupler. So that's the kinematic coupler, I'll call it. But I want to extend that coupler. I'm going to have to make that coupler include this point out here that generates the curve of interest. And the shape of that can be whatever I feel like. But that's the point of interest. Now, in order to determine where that is, I've got two options. I need two coordinates, obviously, to locate a point with respect to another, or with respect to an axis system, right? I need either x and a y or an r and a theta. I think I'm going to call it delta, because I call it that in the book. So we'll call this delta 3. Okay? That's my angle reference to a local coordinate system, which I would call x prime, y prime. That's a local rotating coordinate system in my terminology in your design of machinery book. And this distance, let's give this a name. Let's call this point P. So this would be R of P, position vector P, going up to there. Now, if I had a protractor, which I didn't bring with me today, I could measure this angle delta 3 on here, and I could take my ruler, which I did bring, and I could measure that length. I can find out that RP at this scale should be 6 5/8 inches or thereabouts. Okay, so I already know that this is 6.25 inches. 6.25 inches. I said 6 5/8. Yeah, 6 5/8. 6.625 inches, let's say. But I forgot my protractor, so what am I going to do? Well, it's actually, I didn't really forget my protractor. I deliberately left it home because I knew it wouldn't give me as good a result as if I measured the Cartesian coordinates. It's much more accurate in general to measure lengths than to measure angles. Protractors are not a very accurate device. So I'm going to create a little axis system here more accurately than I did before, freehand, with my triangles, which I did bring. So there is my, I'll relabel that Y prime and move my label up out of here, since I now have a proper axis system there. So now what I'm going to do is I'm going to measure with my rule the XY coordinates of that guy. And that, to reasonable accuracy, is 6.2. So the X is equal to 6.2, and the Y is equal to this dimension right here, which, if I get my head out of the way, you can see what I'm doing. Looks like it might be 2 7/16. Pretty close. Let's call it 2.42. 2.42 inches. Okay. So all I've done then is I've measured this dimension right here as 2.42 inches, and I've measured this dimension here as, what was it, 6.2 inches. And I've now located that in my local coordinate system within the coupler, because it's part of the coupler. Now, when I go to program 4-bar, which I'm going to do in a minute, because I want to put this linkage in there and generate that curve, I'm going to need the polar coordinates. But I did bring my calculator along, so I can take those dimensions and I can find that angle, can I not? So if I take 2.42 and I divide that, that's the Y, if I divide that by X, 6.2, and if I take the angle whose tangent is that number, I find that my angle here is 21.322 degrees, and I could not have read it that accurately with a protractor. Okay, so I now have the data. I know that my link lengths are what I wrote over here, 2.5, 375, 625, etc. And I know that my coupler point is at R is equal to 6.2 at an angle of, what do we say, 21 point, I'm going to call it 32, that's close enough, degrees. Okay? So now I'm ready to go to, leave this atlas and go to my program. But before I do, if we could come back to the atlas page for just a second, I want to point something else out that I haven't mentioned yet, which is very important. This atlas has a lot of information in it, much more so than first meets the eye. I've already described to you how they're plotting these paths of the various points on the coupler of the linkage, and they're changing the linkage dimensions, etc. But they very cleverly did something more than that. You'll notice that these curves are all done with dashed lines, not with solid lines. And the dashes have meaning. Each of the dashes that you see on any one of these coupler curves represents exactly 5 degrees of crank rotation. Actually, to say that more correctly, the distance from the beginning of one dash to the beginning of the next is 5 degrees of crank rotation. Now think about that. If I'm turning the crank at a constant speed, then equal angles are equal time. So if you look at the curve that I just chose, and you look at the relative lengths of the dashes on the back side here versus down here, I can impute a lot about the velocity of that point. For one thing, it's going faster on the backside than it is here, because for the same delta time, which is to say delta angle of the crank at constant speed, I'm moving about 3 times as far as I am down here. That's the first thing that I notice. The second thing I notice is that during this portion of the curve down here, there's relatively little change in the lengths of those dashes. That indicates that I'm very nearly constant speed there. That's desirable. Remember I said at the outset that I wanted something approximating constant velocity to track my conveyor. And I didn't make that point when I first chose this curve. Coming Down here, I'm moving at relatively constant velocity. It's speeding up a little bit there, and then it slows down again as it comes around the corner, and then it goes like the dickens back to my cusp. This would be called a quick return mechanism, if I consider this to be the forward motion and this to be the return. So by just looking at these curves, I can see the relative quick return nature of them. I can see actually impute some crude acceleration information, because as the velocities as indicated by the lengths of these dashes, is changing rapidly, that indicates I have high accelerations. I can't get any real acceleration numbers out of that are worth anything. But I get a very good, holistic, intuitive feel for the way that curve is going to behave when I drive it with a constant speed crank. Okay, enough of that. Let's move now to the program. I'll close that for the moment and go back to the computer over here. And we'll bring the data into program 4-bar, for which purpose I have to interrupt my PowerPoint presentation here and bring back the 4-bar. There we go. So if you've had any chance to use this program 4-bar, then you know what you're looking at. If not, then perhaps you're seeing this for the first time. There is also a videotape on how to use this program. If you haven't learned how to use it yet, you can avail yourself of that. I'm going to go to the input screen here, and this provides me with these boxes in which I can type the dimensions of the links, and I'm going to go back to my, don't have to look at this with me, but I can read the numbers off of my previous paper here. We decided that the crank wanted to be 2.5, which just by happenstance it already is. That wasn't planned. The coupler we decided wanted to be 3.75. I'm tabbing between these boxes. The rocker wanted to be 6.25, I think we said. The distance to the coupler point we said was 6.2. And the angle to the coupler point was 21.32 degrees. And I also have to deal with the ground link. I'm going to do that down here. Now, the program lets me put the ground link at an angle other than 0, and it may not have been obvious to you, I didn't point it out, but the way the Hrones and Nelson is arranged, that ground link was not at 0, it was at some other angle. I don't even know what that angle is at the moment. So I'm going to go to polar coordinates here and just tell it the length of that link. And I'm going to draw it in 4-bar as if it were horizontal. And we can change that later. But that ground link was also 6.25. And that should be enough information to calculate it. Now, over here, I should tell it where to start and where to end. We want to see the whole curve. So I'm going to start it at 0 and go to 360. And I don't think we need 1 degree increments. I'll go in 5 degree increments. And omega can be whatever we like. I'll leave it at 1 radian per second. It's not critical to this discussion. And I hit the calculate. And that doesn't look an awful lot like the curve that I saw in Hrones and Nelson. But you'll notice that this is in the crossed mode up here in the upper left-hand corner. And if you've read Chapter 4 yet, which you may not have at this stage of the course, I take a couple of curves up before we get to that business. But let me just tell you that a 4-bar linkage can be assembled in one of 2 modes. I call them open and crossed. And it's not possible to predict which you have at the outset. And it happened that I had this in crossed mode, and it happens that that one out of the atlas is open mode. Notice when I switch it from one to the other, we get a curve that looks a little bit more like Willie the Whale. That looks like what I want. Now, you recall that in the book, the whale was laying over more on its side here. And maybe I want to make it look like that. To do so, I simply have to tell it what angle the ground link is at. And I measured this earlier, and I think it's of the order of minus 40 degrees or thereabouts. That's in the ballpark at least. So I'm going to tell it to go there and recalculate. And that looks a little bit more like what we saw in the book. So it's laying down in that mode. My pivot has gone off screen down here now. I could correct that by bringing this back up to 0. I just wanted you to see that this looked more or less like that picture in the book. But let's put that back at 0 and get it back on the screen. So I can run this now through its motion with the run command. Let me turn off the centros. I don't need those. And let me also try to slow that down a little bit. That's a little bit better. And you get a little sense of the quick return aspect of this. If I go in smaller increments, that'll be even more obvious. Let me cut that down to 1 degree over here and recalc and then run it. My screen update rate can't keep up with that now. So we're having a little bit of problem with the computer being able to show all of those. Let's go to, that's a little bit better, at 2 degree increments. So now I have a linkage that will give me the kind of motion that I thought I wanted, and the process that I went through was to sketch out what I thought I needed, go into Hrones and Nelson, find something reasonably close to that, extract the information from that atlas that allowed me to come into this program or in some other means, and put in the dimensions of the linkage, essentially, is all it amounts to, and calculate and run it. And now I can analyze this to my heart's content and determine whether or not it will do the job. If it doesn't, I go back to the atlas and pick something else. There's 7,000 of them there, after all, for you to pick from. Okay, let's go back to our PowerPoint and see where we are here. So we just did that. Okay, now I want to talk a little bit about applications. What do we do with these coupler curves? Well, it turns out there's a lot we can do with them, not just that part feeder thingy that I invented for the example before. Here's a real problem that's been solved for a long, long time with a coupler curve. The film advance mechanism in the movie projector at the theater where you go to see the latest flick may in fact have a mechanism such as this. It's a Grashof 4-bar linkage, and it has a coupler point that has a curve of this shape with a cusp. And the idea here, very briefly, is you may or may not be aware of the fact that what we call movies are really not moving. It's a series of still pictures. It's essentially a very fast slideshow, but the slides get put on the screen so rapidly that our eyes consider them to be a continuum, because our eyes, the reaction time of our eyes, our eye-brain combo, is not fast enough to see the individual pictures. I think the rate is about 24 frames per second, and we can't really see things happening that fast. So it appears to us as if it's a continuously changing series of images, but it in fact is not. So to accomplish that illusion, the film projector, and for that matter the camera, must expose the film, in the case of the projector, to the light that's going to put it on the screen for a brief moment. I think a 60th of a second is typical, and then close the shutter so the screen goes black, move the film to the next picture, and then open up the shutter and let it go light again so you see the new picture. This mechanism is what moves the film from one position to the other. So the film is moving, stopping, moving, stopping, moving, stopping 24 times a second. And while it's stopped, the shutter opens up to let the light through for about a 60th of a second, and you see the image, and it remains in your brain long enough that you think it's still there when the next image appears. So this mechanism has a little hook on it, and if you've ever seen film, you know there are holes down the side of the film. So this sticks its nose into a hole and grabs the film and pulls it down in the direction of the red arrow. The film itself is guided in what's called a gate. It's simply a track, so the film has to go straight. So it isn't necessary for this hook to go in a perfect straight line, and it does not. As I mentioned before, a 4-bar linkage cannot give you a perfect straight line, just an approximate one. But it is close enough for this purpose. But at the bottom, you want to back this hook out of the film without jarring the film, because if you give the film a little bit of a tweak on the way out just as the shutter opens, you're going to see your image on the screen jitter. So the cusp is used to back that hook, which actually has engagement with the film hole, back up out of engagement without jarring the film. So the motion then is pull the film down, get out of it. The film is now visible on the screen, During the backstroke, it's wasting time while you're looking at the picture. Now the shutter is closed, the screen has gone black, it grabs the film, yanks it down very quickly to the next position, backs out, the shutter opens, you see the new image. I'll show you a model of that in just a moment. Another very common application of coupler curves is automotive suspension. Here in a figure that's from your book, schematically depicts an automotive suspension system, could be front or rear. 4-bar linkage. Link 2 connects the wheel assembly, which is on link 3, the coupler, back to the chassis, as does link 4. These are typically non-Grashof. I don't think you want your wheels going around in circles in this plane at least. So there's no need to have a Grashof linkage here. The spring and shock absorber not shown are what control its motion and keep it from going all the way up. But in fact, the path of motion of the tire as it traverses bumps is along a coupler curve, actually a whole family of coupler curves, because each point on this coupler, as you now should understand, has a different coupler curve. This is a schematic, actually a drawing of a Chrysler Viper, I guess it's a Dodge Viper, suspension system. This is courtesy of Chrysler. They gave me the drawing. And these are referred to as wishbones. You may be familiar with that term if you've fiddled with automobiles at all. But this is in the upper diagram. This would be my link 2. This is the link 3 assembly. That's the wheel spindle right there, the wheel bearing. There's the tire. And here's what I call link 4 in the picture up above. And the spring and the shock is a little bit differently arranged than I show up above. So there are a couple of applications. Now let me show you a model of this film projector mechanism, which is quite clever. This has been around for, I think, close to a century, as long as movies have been around, which is quite a long time now. So here we have that same linkage, or something very close to it, and I'll prove to you, first of all, I hope, if I can get my pen through there, that my pen doesn't want to go through that hole. So maybe I won't prove to you that this is a Grashof. Well, you can see it goes around in circles. Now, there's an example of a crossed and opened. I just flipped it from one to the other. So the cardboard's a little bit flexible. So let me not be so aggressive with it. I'll be more gentle this time, and I'll move it through. And you can see that my left hand here is driving the crank in a full circle. And the coupler is doing something or other. Let's investigate what the coupler is doing by putting my pin in here. At least that will go through the hole. Let's go the other way, because this is the way it's actually going to go. I'm pulling the film down. I'm at the cusp. I back out of the hole in the film. I come up around the top. I'm on the back, and my hand's in the way too. Let's use my other hand. I'm on the backstroke. And now I'm coming around again. I'm going to pick up on the film again and pull it down. The shutter's closed, the screen is black, you can't see what's going on if you're in the theater. Now I'm down at the bottom here, and the shutter's now opening, so you can see the next image on the screen. I'm coming around the backstroke, wasting time. Shutter's closing, screen's gone black, I pull the film down again. And that should give you some idea of how this works. Very simple mechanism, and it's driven directly off the same shaft that's causing the film reels to turn, feeding the film into the gate and picking it back up, wrapping it up on the reel down below. So that should give you a little idea of a practical use of a coupler curve. Let's go back to our slideshow here. I'm going to change the picture a little bit, I'll change the focus, I guess, to geared 5 bars. Any linkage of any number of links generates coupler curves, assuming it has a couple link, and most of them do. So now we're going to up the ante and go to a 5-bar linkage. And if you have read your Chapter 2 information on degrees of freedom, you should know that if you had 5 bars and 5 pins, you will have 2 degrees of freedom, requiring 2 inputs. And that's not usually what we want. Motors are kind of expensive. I don't want to put 2 motors on and have to have them synchronized to one another and such. So a simple solution to that problem is to connect links 2 and 5, as shown here, with a pair of gears. I can put the motor now either on 5 or 2, and when I turn that shaft, this guy falls along dutifully at whatever gear ratio I provide, and my link 3 and link 4 are both couplers, and I can get an infinity coupler curves off of each, and the point 3, 4 which is the join between the two links, will also generate coupler curves, and that's what I'm going to show you here. There is an atlas similar to the Hrones and Nelson called the Zhang-Norton-Hammond Atlas of geared 5-bar coupler linkages. I have that with me, and I'll show you it in a moment. This is one page from it, which is in your book. And because we have more parameters, which I can show you here, these coupler curves for 5 bars have much more complex shapes than a 4-bar. And the main reason is because we have 3 more design parameters than we have in the 4-bar. We have the additional link ratio, because there is a 5th link. We have the gear ratio as a parameter that can be varied. We have the phase angle between the gears. In other words, I can pick the 2 gears out of engagement, rotate one of them, and drop them back into engagement, and I will get new coupler curves because I've changed the initial conditions, the initial position of one gear with respect to the other. If I provide it with an integer gear ratio, I will get a repeating curve. If it's 1 to 1, it's rather uninteresting. If it's 2 to 1, it'll repeat after 2 revolutions, 3 to 1 after 3 revolutions, etc. If I have a non-repeating decimal ratio for a gear ratio, such as pi, for example, a number that never really settles down, then I will get a coupler curve that continues to change shape in a precessing fashion. Not necessarily practical, but kind of interesting. Let's look at the atlas now and see what it can tell us about these curves. It's arranged in a similar fashion to that of the Hrones and Nelson, but it's much smaller. It also was done much more recently, and so was generated with computer resources, making it a lot easier to do than Mr. Hrones and Mr. Nelson actually built metal linkage models and drew those curves manually, would you believe, all 7,000 of them. So if we can focus in on this upper corner here, much like the Hrones and Nelson Atlas, there's a little bit of information here to tell you what parameters are, what the parameters for this linkage are. Alpha, beta, and lambda are the 3 ratios. Again, the crank is considered to be 1 unit in length. And also, I should mention that this atlas deals only with what are termed symmetrical 5-bar linkages, which is to say that link 1 and link 5 are the same length, and link 3 and link 4 are the same length. So alpha then is the ratio of link 4 or 3 to 1. Beta is the ratio of the ground link 1 to 1 to the crank, and lambda is the gear ratio. And a negative gear ratio indicates that you have a pair of gears, typically, one of which turns the other in the opposite direction. If this were positive 1, it would imply that you had an idler gear present to reverse the rotation so that crank 5 would turn in the same direction as crank 1. So this ratio can be either plus or minus, and it can be either an integer or not, though I think integer is a more practical solution. So a negative 1 ratio, gear ratio, doesn't give curves. If we come back, if we can zoom back out to the page to give you some sense of what the curves look like with that ratio. These are rather mundane. I mean, they look for all the world like they were generated with a 4-bar linkage. Here I have some crew nodes. I have a cusp. I got some, I don't see really a lot of flat stuff, but there's a figure 8 up there. Rather mundane, not too interesting. This shows you the linkage down here in one particular position. That would be link 2, the crank. This would be link 3, one of the couplers. Link 4, one of the couplers. This atlas also only shows you curves at this join between the 2 couplers, and recognize the fact that I could put, let me get a piece of tracing paper, I can expand the either of those links to include a whole bunch of other points, so I can get a lot of variety, and I'm not going to show it to you today since this tape is running too long already. But program 5-bar will let you bring the information from this atlas into it, just as I did from the Hrones into the 4-bar, and you can then create some coupler point over here and generate whatever curve it might make. So again, this is a starting point for determining a linkage that may have suitable properties. before I leave this page, let me point out that at a certain phase angle, these numbers down here represent the phase angles between the input and output gears, the gear on link 2 versus the gear on link 5. The numbers are not too readable at this scale. It's 0, 15 degrees, 30, 45, etc., through 180. So the only difference, the only thing I have to change to go from this curve to this curve to this curve is to pull the gears apart, rotate one, and put them back together again, changing their phase angle. They were all negative 1 gear ratio. With a 180-degree phase angle, I get a perfect straight line, and this is not approximate. This is on the money. So this will generate an exact straight line. Kind of an expensive way to get the straight line because of the gears, but nevertheless. Okay, I'm going to flip through this to get to some more interesting looking curves. I'm still in the -1 gear ratio department here, and that doesn't have very interesting stuff. It looks too much like a 4-bar linkage. Now I'm in +1. And as I show you in Design of Machinery, at some point you can actually generate the same coupler curve that a 4-bar linkage generates with a geared 5-bar linkage that has a +1 gear ratio. This is in Chapter 6 under the topic of cognates. So let's keep going. I want to get to some more interesting gear ratios. We're still in the ones. Here we come to a -2. Now this is starting to look a little more interesting. So this, I won't bother to zoom in on it, but this says I have an alpha of 3.2, a beta of 3.2, and a lambda of -2. So the gear ratio here is -2, which means one gear is twice as large as the other, and there are only 2 of them, so they turn in opposite directions, and thus the negative sign. And now, because of the gear ratio of 2, I have at least 2 loops, it seems, in all of these, and in some cases I have 3 loops. This is bordering on 4 down here. Again, the difference here is phase angle only. So everything on this page has these ratios, but the family shown differs only in the phase angle. And all of them, unlike the Hrones and Nelson, I don't give you a map of these across the real estate of the coupler, but rather just show you that one point. Program 5-bar will give you additional information. So you would take the data out of here in the same fashion. Here is still -2, very similar looking. And if you start using other gear ratios, you're going to get very much more interesting looking curves. Another -2. Here's the +2s, and here's some interesting looking stuff. By the way, the dots here are equispaced just as the dash lengths are equispaced in the Hrones and Nelson Atlas. Therefore, you get a sense of the velocity along the path by the spacing of the dots. Each of these dots is the same crank angle input over here, which for a constant speed input is the same delta time. So notice this is going really fast across this portion because it's going from there to there in the same time that it takes to go from there to there on this part of the curve. So there's a huge quick return ratio in this curve. So if you need some very crazy motions in your machine to pick something up and place it over here and turn it upside down or whatnot, these linkages have some potential. Quite a large variety of curves. I'll leave it to you to figure out how to get the data out. It's very much like the Hrones and Nelson. Okay, let's move on in the interest of time and go back to our slideshow, which is just about over. Here's a summary of what we've talked about today. The couple of curves of simple linkages, I'm talking about 4-bar and geared 5-bar here, can provide very complex and interesting motions. We can use those for path generation, which is what we've been looking at today. By that is meant I'm moving a point along a path. I'm not, at that instant, when I'm considering path motion, I'm not really concerned about the orientation of the link. That, however, could be a serious issue. And I can deal with that by introducing duplicate linkages or cognates of the same linkage, and then I can get what's called parallel motion, in which I control a line in the plane to follow the path of interest, which would be the coupler curve, and every point on that line follows the same path, thus the parallel motion terminology. And I can also use coupler paths to make dwell mechanisms, and that's the subject of another tape. Thank you. We'll see you on the next video.